Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we'll be doing Unit 4, Lesson number 5, on the method of common basis. So, there aren't a lot of algebraic techniques that go along with exponential expressions and exponential equations. But one of them that we'll learn today is what's called the method of common basis. Students love this, as long as they're comfortable with basic powers, basic exponent work. So let's jump right into it and see how it works. All right, exercise number 1. Solve each of the following simple exponential equations by writing each side of the equation using a common base. Remember, a lot of students like to ignore terminology, but this is the base. So right now, literally, we have the equation 2 to the x equals 16 to the first, if you will, but they don't have common bases. One of them has a base of 2. One of them has a base of 16. But you see 16 can be thought of as 2 to the fourth. So if we rewrite this as 2 to the x equals 2 to the fourth, then we can say x must be equal to 4. Right? The idea is very simple here. If the bases are the same, then the exponents must be the same. Okay, this is due to the fact that exponential expressions are, or exponential functions are one-to-one, meaning that that if the exponent, if what the exponent is gives you the same output, then the exponent has to be the same. I don't know how well that really turned out, but let's keep going. These first few are quite simple, right? 3 to the x, we want a common base. 27 is 3 to the third. Therefore, x equals 3. Now you might just say to yourself, well, look, I know 3 to the third is 27, so x is 3. That's great. Let's look at one that's more challenging. Here we have 5 to the x. Here we have 1/25. Well, one thing I know for certain is that 1/25 is the same as 1 over 5 squared. So that means we have 5 to the negative 2, and therefore x is negative 2. Ooh, now up to this point, each time we looked at the left-hand side, that was the base we used. On the other hand, here we might look at the 16 and the 4, and the first thing that might occur to us is that 16 is the same as 4 squared. So I have 4 squared to the x is equal to 4. Now I can use that property of exponents that says, hey, let's multiply these two together, and I get 4 to the 2x is equal to 4 to the first. That means I can now set my 2x equal to 1 and get x equals 1/2. All right. Now, some of you that really picked up on that whole fractional exponents thing could have also said, well, look, I can use 16 because I know that 4 is the same as 16 to the 1/2. So you could have easily used 16 as a base. If you said, okay, I got 16 to the x equals 16 to the 1/2, then x equals 1/2. All right. But if not, you go with the more common base, which is 4. All right, take a look at what we've done. Pretty easy, maybe so easy that you don't really see the point. And then we'll go on to some that are a little bit more challenging. All right, I'm going to clear this out. All right, exercise number 2 says simplify each of the following exponential expressions. Notice, none of these are equations. I'm not asking you to solve any equation, I'm just asking you to simplify these. So pause the video for a minute and ask yourself, how can you simplify these exponential expressions? All right, well, in each one of these cases, we're using the exponential rule, or exponent rule or property that says when we have something raised to an exponent, raised to another exponent, we simply multiply the two exponents. So we have 2 to the 3x. Here, we'd have 3 to the 8x, 2 times 4x. Here, we'd have 5 to the negative 3x plus 7. Because remember, we're going to have to multiply these two exponents together, so they're going to distribute. And likewise, here we'd have 4 to the negative 3 plus 3x squared. Nothing very special about this particular problem. You might even wonder what it has to do with what we're doing in this lesson today, but we'll get to that in just a moment. This exponent law is going to be critical for what we're doing next. So let's take a look at some method of common base problems that are a little more challenging. I'm going to clear this out, so pause the video if you need to. All right, here we go. All right, solve each of the following equations by finding a common base for each side. All right, so I take a look at this equation and I look at the 8 and I look at the 32 and I try to come up with a common base. Now, for me, what I know is that 8 is equal to 2 to the third, and I know that 32 is equal to 2 to the fifth. So I'm going to use 2 as my common base. So I'm going to write 8 as 2 to the third, but then that's being raised to the x. And then I'm going to write 32 as 2 to the fifth. Now I'm going to use that great property of exponents that we were just reviewing, and I'll get 2 to the 3x is equal to 2 to the fifth. That means at this point I can say that 3x is equal to 5, and x must be 5/3. Now, I want you to keep in mind what we're not doing. We're not canceling the 2's or anything like that. We're not doing that, okay? We're just recognizing the fact that if I take 2 and I raise it to a number, I take 2 and I raise it to another number, if those two things are equal, then the two exponents have to be equal as well. We're not canceling the 2. All right, let's take a look at letter B. What's going to be the common base here? Think about it for a moment. All right, well, hopefully you figured out it would be 3. You see 9 is equal to 3 squared. 27 is equal to 3 cubed. So we can write this left-hand side as 3 squared to the 2x plus 1, and we can write this side as 3 cubed. Again, I can use that great property. Whoops, apparently I can use it incorrectly. I can use that great property that allows me to now multiply these. Don't forget to distribute that 2. So it's now going to be 3 to the 4x plus 2 equals 3 to the third. Once I have those common bases, I can, if you will, drop them, not cancel them, but just drop them. And I'll get 4x plus 2 is equal to 3, 4x is equal to 1, and x is equal to 1/4. Isn't that great? Okay, letter C is more of a challenge, but why don't you pause the video and see if you can pull it off yourself. All right. Well, hopefully you figured out a good common base of 5. You could probably do other common bases, but a common base of 5 works out well. It works out well because 125 is 5 to the third, and 1/25 is 5 to the negative 2. So we're going to say 5 to the third, all raised to the x, is equal to 5 to the negative 2, all raised to the 4 minus x. Again, just using that property of exponents, multiplying them, gives me this. And now that we've got that common base, I can get rid of it, and I'm sure you can finish it out. Isn't that cool? Now, let me be very clear about something. Really clear about something. All right? If I had something like this, let's say 5 to the x equals 8, this method would be fairly useless. Although not impossible, it is extremely difficult to write 5 and 8 with a common base. Pretty difficult. It can be done. I don't want to claim it can't be done, but it is very, very difficult. So generally speaking, this method only works if there is that convenient and relatively obvious common base. So look for bases like 2, 3, not so much 4, because then you probably would have a base of 2, but 2, 3, 5, 6, 7, etc. All right, pause the video now, and then I'll clear the text. All right, here we go. Let's take a look at a multiple choice problem. Which of the following represents the solution set to 2 to the x squared minus 3 equals 64? Well, play around with this one a little bit. See what you can get. All right. Well, when the number on this side is prime, which 2 is, pretty much that has to be the common base. And it is, right? 64 is 2 to the 6th, if you think about it. Now that we've got our common bases, we're going to get x squared minus 3 is equal to 6. Add 3 to both sides, we're going to get x squared equals 9. Take the square root, and remember we're going to get both a plus and a minus root when we do that. X equals plus or minus 3. And both are completely valid. And of course, you can check these equations. Easily check them like every other equation. If I took, like, let's say the x equals negative 3 root, and I checked, right, to see whether or not this was true, I could take that negative 3, square it, subtract 3, right? That would be negative 3 squared, which would be 9, minus 3, 64. And then I'd get 2 to the 6 equals 64, and that checks. All right. So the method is pretty straightforward. On the back side of the sheet, there's always a back side of the sheet, we're going to be using it to solve some other problems, maybe some higher order problems, but essentially that's the technique. Find a common base for both sides of the equation, manipulate, and set exponents equal. Pause the video now and write down anything you need to. Okay, here we go. All right, two exponential curves, y equals 4 to the x plus 5 halves and y equals 1 half to the 2x plus 1 are shown below. They intersect at point A. A rectangle has one vertex at the origin and the other at A as shown. So that's not a square, it's just your garden variety rectangle. I suppose it could be a square, but I don't think it is. We want to find its area, so we're going to try to figure out the area of this rectangle. Letter A says, fundamentally, what do we need to know about a rectangle to find its area? This is easy enough. Pause the video for now and write down what you need to know to find a rectangle's area. All right, well, I don't care how you phrase it, you got to know its length and width, or its base and its height. I almost spelled the word height wrong. That'd be embarrassing for a math teacher. All right, well, letter B. How would knowing the coordinates of point A help us find this area, or the area? Well, think about that for a minute. If I knew the coordinates of point A, how would it help me find the area? I wonder. Well, let's talk about it. Now, the y-coordinate would simply be the height. And the x-coordinate, well, it would be negative, obviously, from the picture, so maybe its absolute value would be the base. All right, it says find the area of the rectangle algebraically using the method of common bases. Show your work carefully. Oh, I get it. You see, I need to find that intersection point. So I need to solve this equation. 4 to the x plus 5 halves is equal to 1 half to the 2x plus 1. Well, what I'd like you to do is pause the video now and try to solve that to find the value of x. Then think about finding the value of y as well. All right, let's do it. Shuffle my notes a little bit so that I can make sure I see the proper answer at the end. Well, the common base is a base of 2. 4 is 2 squared. So I'll write that. 1 half is 2 to the negative 1. All right, doing a little simplifying, we'd get 2 to the 2x plus 5 is equal to 2 to the negative 2x minus 1. I almost forgot to distribute that. Now I can set those two exponents equal, and I'll get 4x is equal to negative 6, and x is equal to negative 3 halves. All right, fair enough. Let's figure out what y is equal to. I think I'll go with this one. Y is equal to 4 to the negative 3 halves plus 5 halves. Be careful, those are all in the exponent, which would be 4 to the 2 halves, which would be 4 to the first, which is 4. So we now know the coordinates of that intersection are negative 3 halves and 4. But that means its area is going to have a base length of 3 halves, a height of 4, and we're going to have an area of 6. All right? This is totally the kind of problem that I could see being maybe even upwards of a 6-point problem on a Common Core assessment like the New York State Regents. Granted, I doubt there'd be Part A and Part B, but there could be. Most of the time, though, you'd have to just simply know, well, if I find that intersection point, it's going to help me find the area. Pause the video now and write down anything you need to. All right, great. Let's clear it, and let's move on. Okay, one more problem, little multiple choice here. At what x-coordinate will the graph of y equals 25 to the x minus a intersect the graph of y equals 1 over 125 to the 3x plus 1? Show the work that leads to your choice. All right, so notice all 4 choices have x solved for in terms of a. That makes some sense, all right? So why don't you pause the video and see if you can figure out which one of these is the correct choice. All right. One of the things I like about this problem is, although not impossible to use your calculator, if we didn't have that x minus a there, if we had x minus 3, well then you could really put the two things in your calculator, graph, use your intersect command, etc. to find the intersection. Here, though, to find the intersection, we're going to set the two equations equal. And we're going to use the method of common bases. Now that common base is a base of 5. We've seen both of these a couple times today. 25 is obviously 5 squared to the x minus a. 125 is 5 to the minus 3. All right, so there we got our common base of 5. When we distribute those inner powers, we get 5 to the 2x minus 2a is equal to 5 to the negative 9x minus 3. We've now got our common bases. So we're going to set 2x minus 2a equal to negative 9x minus 3. Remember what we're trying to do here. Never lose sight of what you're trying to do. That can happen in math often, right? We're trying to solve for x. So I'm going to bring this negative 9x to this side. It's going to give me 11x minus 2a is equal to negative 3. And then I'm going to add a 2a to both sides here. And that's going to give me 11x equals 2a minus 3. But now, of course, it's easy enough to just divide and get x equals 2a minus 3 divided by 11. Choice 2. All right. And that's it. All right, so the method of common bases, not too bad. Pause the video now, write down anything you have to, and then we'll wrap up. Okay, here we go. So as I mentioned at the outset, there are very few algebraic techniques that really allow us to work with exponential equations. The method of common bases is a very restrictive method, meaning that it doesn't work very often, but when it does work, it's really neat. And it works when you can look at two sides of an exponential equation and write both sides with the same numerical base. If you can do that, then the method of common bases works great to help you solve exponential equations. For now, I'd like to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.